So during the last two lectures, we introduced the idea of an infinite degree of system free of infinite degree of freedom system, and today we're going to actually describe how to solve it. So just to remind ourselves, if we have a material block, let's say like this, and let's say we electroded this side and the other side, and then we apply some alternating electric field to it. It's going to tend to want to vibrate this way. In its vibration, it's not going to be uniform. It's going to look like this, kind of in a sine format. And this is a displacement, and this is position. And we'll draw the middle line 0, starting from the middle. So now, how do we solve this? And I mentioned that the equation describing its motion can be written like this. But really, in order to apply this equation itself, we need to be looking for a transient solution. So this equation actually, it can solve for a transient solution. But after we excite the ceramic with a certain electric field, and we let the let the system die down and let equilibrium, and that's really what we're interested in. And this equation doesn't necessarily we don't need it to find equilibrium conditions. So I'm going to go through a derivation now. We're going to apply an alternating electric field to the piezoelectric material. And I'll start actually a new page for this. So we have an alternating electric field, so I'll apply. A voltage, which is time dependent, which is in this form. And a lot of times we write the sinusoidal, and basically it's a sinusoidal form with some frequency. But we tend to write this part of the equation as this because it really simplifies in the taking derivatives and making the equation simpler. But at the end, what we do is we take the real part. So whatever solution we get, we take the real part, and we end up getting some sign coming out of it. Or something like with a phase, I mentioned earlier, we get some sign with a phase. So this is basically like a trick to solve the equations really easily. So this is what we're going to use. So we apply an alternating voltage or electric field, and we look at our material again, and therefore, since we applied this type of electric field, we're going to say the solution. So a very common method of solving equations is actually you assume a solution. And this equals A cosine kx plus B sine kx e j omega t. So it's time dependent and it's spatially dependent. This k right here is a ratio between the omega, which is the frequency we're forcing at, and v. And v, which we're going to call the sound velocity, is equal to 1 over the square root of the density times the elastic stiffness. So so we're kind of having, you can kind of see now there's like a proportional term. We're kind of making things non-dimensional, and that is a typical method which is used to make equations simpler to solve and understand their significance. So we have this equation, the solution for the equation, and now we're going to apply boundary conditions. And actually, since this takes care of the time dependency, we can just maybe add some phase if you want. But since this takes care of the time dependency, we really don't need to include the time dependency here. Because what we're actually looking for is the solution, is the amplitude. So I mentioned that before we had the displacement profile like this around the resonance frequency. Really, this is like an amplitude. So over time it'll get smaller. It'll keep the same shape but the amplitude. So it'll be some solution, and it'll be some amplitude times the t. It'll be some sine something or other. It'll be an amplitude times t, and this amplitude will just vary the amplitude of it, and it's not going to vary the shape. So what we're actually interested right now is what is the maximum amplitude. And in order to find the maximum amplitude, it's not important to consider the time dependence. So therefore, we're not going to do it. We're going to consider the we don't need to consider the time dependence here. What we can do now is we need to apply the boundary conditions here. So I mentioned at the edges of the plate we don't have any stress, and I mentioned in the middle, since it's uniformly expanding, the material is uniformly expanding, we have no displacement in the middle. It's uniformly expanding about the center. This is, remember, this is a displacement in this position. So it's uniformly expanding about the center. So we have two boundary conditions. So boundary condition number little a, that is the displacement at 0 is 0. Basically it's vibrating, it's extending, but because the left side is extending the same as the right side, we get no net displacement in the middle. And the second boundary condition is the stress at plus or minus L/2 is equal to 0. And we remember from our piezoelectric constitutive equations that if we invoke them and we assume, okay, what's the strain at plus or minus x minus 0, so this ends up being 0 because at that point. So we get dE, which is none other than the d times the voltage over the thickness, the maximum voltage applied. So because that's the case, we can apply these two equations. If we apply equation A, U0 equals A cosine K0 plus B sine K0 equals 0. This is 0. So basically what we end up getting is A equals 0, and this is 1. So basically A equals 0. So automatically we had this equation right here, and we can just eliminate this term completely. Now we invoke the other thing. We have the strain, which is the derivative of u with respect to x, which is now going to be derivative with respect to x of b sine kx. And we can just bring along this guy here if we like. If we choose to bring along him, then we'll have to assume this voltage is a EWJT, and this will end up canceling out, as you'll see in just one moment. So we have this equation now. So we do that derivative, we get B K cosine K X E JT, and this is obviously in the parentheses, and then basically what we do is now we apply the condition. So derivative of u divided by dx at plus or minus L/2 is equal to d VO H, and then we can write EJ over omega t if you want, and then this equals B K cosine K plus or minus L/2. But since in this equation it's a cosine, and cosine of a plus and cosine of a minus is the same thing. because it's a even function. So we'll just reconstruct L over 2. And this e j omega t is there. It'll cancel out right here. And then what we end up with is d v. Well, we end up with what we want to do is we want to solve for b, so we can find the final form of the solution. So b equals d vo divided by t cosine k L over 2. Therefore, the final solution, basically the amplitude, the maximum amplitude occurring, is going to be equal to, remember, b cosine b sine. So what basically what we end up with is d v sine kx, and the sine kx came from the original part, sine kx, all divided by kt cosine 1/2 kl. And this tells us the displacement for a frequency, and obviously the frequency is kind of hidden in this term right here, this k term. We notice if we examine this part tells us some of the amplitude, and this part tells us the relative. So this top part, the sine kx, it tells us as we move along the material. Let's say we have this material about like that. As we move along, how will the strain change? How will the displacement change? And the other thing that we can look at is this cosine term. And this cosine term, let me just draw this as the strain term, and this will change the shape as we move along. So I'll show you frequency plot basically. So when this cosine term right here becomes infinity, so actually I'm going to discuss the meaning of this term later in the next lesson. Thanks for watching.